Mr. Covey here, and this is the first video for our kind of next big chunk of the class. And before we even talk about what we're going to be learning, I just want you to take about a minute and answer this question. I'm telling you, f prime of x, the derivative of f equals 2x. Just tell me about f of x, the original function. Okay. Would you pause, take 30 seconds, a minute, think about that. Okay. I think most of you guys probably said this. You probably said, hey, I know what f of x is. F of x is x squared. Why? Because when you do the derivative of that, you use your power rule, you'd get that the derivative was 2x. But I'm going to challenge you there, and I'm going to say, is that the only possible function that f of x could be? Think about it. Well, no, actually, f of x could be x squared plus, oops, sorry, I guess, 2. Because if f of x was x squared plus 2, then the derivative would still be 2x. Or it could be f of x plus 7. Or it could be f of x minus 36. How many different possible f of x's are there that have derivative 2x? Infinitely many, right? It could be any constant number added on at the end here. Now, let me be clear, it has to be a constant, f of x plus 3x. No. Then the derivative would be 2x plus 3. It doesn't work. So it can only be x squared or differ from x squared by a constant, or be a vertical shift of that x squared function. Okay? When you're trying to find a function that has this derivative, you're doing the opposite process of differentiation. Okay, going in this direction. Let me draw a better picture of this. Much better. All right, so if you have a function f of x, and you take the derivative of it that is called differentiation, you get 2x if your function was of this form, x squared plus some number. Now when you go backwards, you have the derivative and you want to find the original function, we call that anti-differentiation. It's the opposite of differentiation. When you see a picture like this in math, you should think inverse operations. Anti-differentiation is the inverse operation of differentiation. It undoes differentiation. But there's a caveat. And that caveat is what we just mentioned. Because in the process of differentiation, constants go away. When you do anti-differentiation, you don't get out a definitive answer. You get out a form that you know the original function looks like, but you can't nail down the specific original function. Instead, you get this with some constant at the end. Okay, and that's what that plus c there represents. It represents that any number could be there. You a lot of times, well, it's saying c because it's a random constant is what it stands for. And we'll talk more about that in a second. But you see this called a family of functions. Okay, so when you do anti-differentiation, you don't get out a single answer, you get out a family of functions. The reason they call it a family of functions is that they're all related, right? Your function is going to look like x squared, but it could differ by a constant. It could be shifted up or down. If you want a visual of this idea, the red function is 2x, and the blue function is the antiderivative of 2x. It's an antiderivative, so it's x squared plus something. And as you see, if you change that plus something, it vertically shifts the graph up. But remember, when you're thinking about the derivative of the blue function being the red function, you're thinking about the slope of the tangent line. So if you look at this blue graph and think about drawing a tangent line at this point, and you think about now this function and drawing a tangent line at that point, the slope of that tangent line is going to be the same. These two graphs, all of these graphs, this whole family has the same derivative because the slope of the tangent line at any given point is the same for all of them. Moving the function up or down doesn't change the slope of the tangent line, so it doesn't change the derivative. Okay, I hope that makes sense visually. A couple of other notes. A lot of times when you do this and you say f of x equals 2x and you want the antiderivative, if the original was just called f of x and you want to do the antiderivative of that, a lot of times you call it big f of x. Okay, so you use lowercase for the original function and a capital to represent the antiderivative of it. Okay, a couple other comments. Sometimes you hear people talk about differentiation and anti-differentiation, but anti-differentiation has a formal name, and it's called integration. Okay, that's far more common to hear than anti-differentiation. Is what you're doing is integration. You're finding the integral. Okay, and specifically right now what we're doing is finding the indefinite integral. Why are we calling it an indefinite integral? We'll talk about that once we learn more. It's too soon, so don't worry about it. But right now we're doing anti-differentiation, also called integration, and specifically we're doing indefinite integration. We're finding indefinite integrals, which are antiderivatives. And you don't get one antiderivative, you get a family of functions, because there's infinitely many functions that have this as their derivative. And they all differ by a constant and form a family of functions. Isn't that nice how everything kind of comes together like that? It's nice. All right, so if you go and look in your note packet, this says a lot of what we've been saying. You can look at it if you want, but it's been saying everything we've been saying. The nice part about learning integration is it's the opposite of differentiation. So you can pretend like there's a bunch of new rules, but there's really not. If you know how to do the derivative, then how do you do the indefinite integral? You do the derivative backwards, okay? You can make a bunch of fancy rules if you want, but I don't like to do that. I like to just use my brain. Okay, let's do one together. Let's say my function was 2x squared. So I guess. And I wanted to find the antiderivative, the family of functions that has a derivative of 2x squared. Well, if its derivative is squared, then the original must have been cubed. I know that. And then when I'm trying to think of the constant out here, I'm just going to use my brain. You bring down a 3, and you multiply whatever was there by 3 and end up with 2. What times 3 is 2? 2/3 times 3 is 2. Right? And I can easily check that just by doing the derivative and check that I get back there. Okay? Now it's important when they're asking a question like that you throw down a big plus c. And that plus c reminds everybody that there's infinitely many functions. We don't know which original function you were talking about. There could be any number there. And that's called the Covey constant. Okay? You got to remember to put the Covey constant at the end. Okay? Don't forget it. Otherwise, you're acting like it has to be just 2/3 x cubed. But it could be 2/3 x cubed plus 7, 2/3 x cubed minus 2. Okay, make sure you remember that. Let's do a couple of these together real quick. If this is my derivative, x to the 13th, what was the original? Well, it had to be x to the 14th. How come there's no constant? Well, the constant no coefficient. Well, the coefficient must have been 1/14. And don't forget the Covey constant. Square root of x. Well, let me rewrite that as x to the 1/2. The antiderivative, the indefinite integral, must have had an exponent of 3/2. And the coefficient must have been 2/3. Don't forget the Covey constant. 1/x. Okay, so it's x to the -1 it's the negative first. What's 1 more than -1 is 0, but x to the 0 is 1. This one's a tricky one. You paying attention? You almost stopped listening. What has a derivative of 1/x? ln. Don't forget about that. Okay, it's a little tricky one. Let's just do one of these. What has a derivative of secant tan? Secant. So the antiderivative of secant tan is secant of x plus whatever the Covey constant is, plus that c. Okay. Flip the page. There's a symbol that they're going to use when they want you to find the antiderivative. It's called the integral symbol. Okay, so if they want you to find the integral, the antiderivative, they put this little symbol here. It's not an S, it's longer and skinnier. That's kind of a bad one. More like that. Okay? And it says, hey, find the antiderivative of this function. You'll notice this thing here, we'll talk more about that there. For now, I just want you to note that there'll be a d something, and the variable in the d something will match whatever variable the function is written in terms of. So if they wanted you to do the indefinite integral of cosine of theta, they'd put a d theta there. And you'd say, what has a derivative of cosine? Well, sine has a derivative of cosine. You make it a sine of theta because they're telling you the derivatives in terms of theta. And then you put the cubby constant on the end. Okay? Again, don't freak yourself out and act like, oh my gosh, I have to learn all these integration rules now. No, 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 no. You already know this. You already know this because these are derivative rules backwards. You know the derivative of tangent is secant squared. Well, then the antiderivative of secant squared is tangent. You know that. The antiderivative of cosecant squared is negative cotangent because the derivative of cotangent is negative cosecant squared. You already know this, okay? So this isn't a whole new set of rules to learn. This is slowing down, using your brain, thinking backwards, okay? And you're going to have to take it slow at the beginning, but you guys are going to get a hang of it. If you wanted to make it all formal and fancy, you'd say this was the power rule for integration. It's power rule backwards. Instead of the exponent getting smaller, it gets one bigger, and then you need to balance out whatever the coefficient was by dividing by this new exponent. Okay? But again, I don't even think about this personally. I think about working backwards versus, in terms of doing the derivative, which is something I already know how to do. I'm just doing something I know how to do backwards. Okay. For now, again, I mentioned we're calling this indefinite integrals. That's because we don't know the plus c. That's one way to think about it for now. Okay. Now, if we did want to narrow down what the original function was, we could very easily do that if they told us, hey, find the antiderivative of this function, and oh, by the way, it has to go through this one particular point. So as soon as they give us one point that the original function, that the antiderivative, that the indefinite integral went through, we could narrow it down from that family of infinitely many to a single one. Okay? And we're going to do that right now. Okay? So this is kind of cool. We're going to solve a differential equation. I know what you're thinking, differential equations are really hard. It's this crazy class that you're going to take in college. It's going to be your most fun class you ever take. Probably true. But all a differential equation really is an equation that involves derivatives. So instead of just involving variables instead of just involving variables themselves, it involves a relationship between functions and their derivatives. Any equation that has a derivative in it is a differential equation. Okay, there's tons of different types, and that's why there's several college classes that you can take on differential equations. We're going to solve really basic differential equations in BCCO. And the ones we're going to look at are going to look like this. They're going to tell us dy dx equals something, and we're going to find out the original function. They're going to tell us the derivative, we're going to find the original function. Okay? The original function y in this case. Watch this. How are you going to do this? Pretty straightforward. First, if they're telling us the derivative, well, then we have to go backwards. We have to do the antiderivative. Now remember, before you do the antiderivative, there has to be that little dx on the outside, excuse me, on the end of it. And luckily that dx is right here. So what you're going to do is cross multiply that dx over. And so then you're going to have some function. You're going to have that dx, which you need, and you're going to have dy. And then you're going to integrate both sides, do the antiderivative of both sides. You're going to end up with y And the reason you end up with y there is because there's a little 1 here. What has a derivative of 1? Well, just like x, but they're telling us it's in terms of y, so it would just be y. And then you do the antiderivative of little f and get big F, whatever the antiderivative is, and don't forget the Covey constant. Okay, that's the general process here. That first step here, people like to skip. We'll talk about it. It's really important. That kind of like get the dx over there and keep the dy there. People skip that step. We'll talk about that. Anyway, this is not bad. Ready, watch. Find the equation of the curve. Goes through this point. If its slope is given by that. So they're telling us the derivative. This is a differential equation. They're not telling us things about variables or the functions. They're telling us things about the derivative. It's a differential equation. This is not going to be bad at all. Ready? So we're going to multiply over the dx. We have to find the original function from the derivative, so we're going to do the antiderivative. We're going to do the indefinite interval. What you do to one side, you do to the other. That doesn't change. What's the antiderivative of 1? Well, it's just 1, or it's just x, but in this case we're doing it with y, so it's just y. Now I actually have to do the antiderivative of this polynomial. Okay, instead of having an x cubed, it's going to go up 1 instead of down 1. What would be here so that when the 4 came down, it'd end up being 2.5. Take your time if you want. That x term, the original, the antiderivative must have been squared, and there must have been a 3 to end up with 6x. Minus 5x, because minus 5x's derivative is negative 5, plus my Covey constant. Okay? But this is a family of functions. There's infinitely many functions that have this derivative. But as soon as they tell me it goes through this point, I can actually figure out what the Covey constant is. How? By plugging that point in. So if I plug in negative 3 for y, and I plug in 2 for x, and I solve this equation, 8 plus 12 minus 10 plus c, 20, 10, then I actually figured out the solution to this differential equation. I figured out that the only function, sorry, let me, oops, that was to the fourth. I figured out that the only function that has this derivative and goes through this point is this function. So that is the one solution to that differential equation. They call this a particular solution to the differential equation, as opposed to a general solution. It's a particular one. This is the only solution there. And oh, by the way, I should mention that too. This little like point they give you, a lot of times they call that an initial condition. So if you want to be fancy and show off your knowledge of differential equations to people, you can be like, oh yeah, because they gave me an initial condition in that differential equation, I was able to find a particular solution. Pretty fancy. Pretty fancy. All right, here's just 4 standard find the indefinite integral, find the antiderivative. Okay? Remember, I haven't mentioned this, but I hope you thought of it. Hey, if you're not sure if you did the antiderivative right, just do the derivative to check it. This is great because the process of differentiation of finding the derivative is easier. So it's nice that the check is easier than the actual problem. Okay? We'll do one of these together and then I'll let you try and figure out the other two. All right. Again, this symbol means find the antiderivative. Find the antiderivative of that. Well, it must have been an x to the 4th. What was the coefficient? I actually think the coefficient was just 1. Must have been an x cubed, and there was a 2. Must have been a minus x. And don't forget the Covey constant. Okay, you have to put the Covey constant. These next 3 are a little trickier. Remember some of the ideas you used when you first learned how to do derivatives. Simplify stuff to make it look nice and neat, and it will help you do the antiderivative. Okay, pause, give those a try, and we'll go over them in a minute. Okay. So for the second one here, rewrite it. like this. Okay, my rule that I always say about, or my idea that I always say about when you're learning derivatives at first, get it to be number x power, and then it was easy to do the derivative. And the same thing is true for antiderivatives. If you can get it to look like number x power, then doing the antiderivative is easy. So if possible to simplify it to look like that, do that. And that's what I did here. Okay, so then I got this is my antiderivative. Don't forget the Covey constant. For this one, I bet some of you guys tried to do this. You tried to like take each individual one and do the antiderivative of it. But if you do the derivative of this, you do not get this. This is completely off. So if you're trying to do the antiderivative of a quotient, it's gonna be complicated. Just like doing the derivative of a quotient is complicated, doing the antiderivative of a quotient is complicated. We'll learn about it. We got a long year ahead of us. There's ways to do it, but for now, I don't need to deal with that because I can, just rewrite it like this. And once I rewrite it like this, I should leave my integral because I haven't done it yet. Then I can do the antiderivative using my reverse power rule. Be a little careful about that. The negative exponents get a little tricky. What's 1 more than -4? -3. Be careful. Okay. Last one here. Again, how do you do the antiderivative of a product? Very complicated. We'll talk about it. But I don't have to deal with that because I can distribute this. And then the products that I end up with, like secant tan, will actually know what has a derivative of secant tan. Secant does. Okay? And here's my antiderivative, here's my indefinite integral, and don't forget the plus c. That's the first lesson in a long chapter and multiple chapters on this process of integration. So thanks for watching. We'll practice this a lot. Don't worry.